Hey guys, welcome back to another episode of Intelligence Maxing. So, it's day 55. Currently going to work on some flashcards for one of my classes. I think it's my deep learning class, so gonna be working on that for a little bit and see how far we get. Maybe look at some other slides too, just so we can kind of understand. I'm a bit behind in the class, some complex topics that are not super clear, so I'm going to try to review this, but let's get into it. Okay, so what are 3 things that CNNs do to help make image classification practical? I think this refers to the idea that convolutional neural networks, they first reduce the number of parameters a neural network needs to learn, and that's through the idea of using a filter. And that filter has a lot less parameters compared to a fully connected network. Then you also have the idea of those filters can help you learn the correlations between pixels. Usually with pictures, you have pixels, and the pixels that are nearby the other pixels will tend to have similar values. I think Josh Starmer gave an example of if you had a picture of a teddy bear, you choose a random you choose a random pixel on the image. If it's brown, then choose pixels right next to it. They're also likely to be brown too. And I think the last one is that if you were to use a convolutional neural network, I think even if you make shifts in the image, then that shouldn't have a big effect on the image classification. That's pretty good. Cosine similarity. What example does StackQuest give? So I think mathematically, cosine similarity is a way of measuring how similar two variables are based on the dot product. I think specifically a dot product that is standardized, meaning that we divide by the standard deviation to make it between 0 and 1, or maybe -1 and 1. But it is a measurement of how similar data points are. And cosine, you can think of that as the cosine wave, and also a measurement of the adjacent over the hypotenuse, which I feel like could be, it could be like a projection of the vector onto the other. Okay, what example does StackQuest give? So StackQuest, he gives the example where I think you have 2 variables, one for some type of cell or protein in a cell and another for a different type of protein. What he did was he graphed them on a 2-dimensional axis, and I think ran a regression. Let's see. Oops. Relatively easy to calculate metric that can tell us how similar different things are. Okay. Yeah, so that was tough. What does StackQuest say is a better alternative to assigning words or a number to be fed into a neural network? Just use a word embedding. Train a neural network to embed a word for you. Okay. what is the idea of padding? What is zero padding? What does zero padding ensure? So the idea of padding refers to just adding more blocks to a convolutional filter. What does zero padding mean? That means making enough padding or adding enough padding so that the inputs to a convolutional layer is the exact same size in terms of its output or the feature map. Center of the kernel, filter will touch. Okay. How does cosine similarity work mathematically? What are the steps? How many are there? Okay. I think one way to think about it mathematically is maybe to take one example and another example, try to find the cosine of the angle between them, store that cosine, and then maybe you just keep adding those over and over again. Cosine similarity is calculating the cosine of the angle between two vectors that represent a count of the number of occurrences for a word in each phrase. That represent a count of the number of occurrences for a word in each phrase. Okay. Let me see what I mean by this. So, calculating the cosine of the angle between two vectors that represent a count of the number of occurrences for a word in each phrase. This is make a table of word occurrences, plot the points, figure out the angle, calculate the cosine of the angle. So I think maybe we have an x and y axis. X representing the number of occurrences in one word, Y number of occurrences in another word. Just plot that. Oh. So this is, in the 2D case, I think that means that a phrase has two words. What is the first stage of a LSTM neural unit for get rate? I think the first stage works by determining how much of the long-term memory should pass through in the neural network, or specifically the neural unit. Does that by taking in an input and then also short-term memory, applying some type of linear activation, and then passing that through a sigmoid function. That sigmoid function will output a percentage, 0 to 100%, and then that'll be multiplied onto the long-term memory. That multiplication kind of scales and determines how much of the long-term memory should be passed through. is a simple, naive way to turn words into numbers, just randomly assigning a word to a number. Any problems with that? There could be where you have a word that, say, large, and a word big, and they got randomly assigned drastically different numbers. One is positive 1,000, the other is negative 1 million. Then with a neural network, it might be difficult to associate these two words that are very similar together.
I'll talk to anybody that doesn't know. People go.
Okay. Word associations, right? Maybe when we're working with this transformer-based model, we have to calculate this idea of self-attention, and self-attention is, I mean, maybe you can scale your input by some value, some weight, but yeah, I'm not entirely sure. So cosine similarity, an example the StatQuest gave. Cosine similarity is the idea of measuring how similar two phrases are, or maybe two vectors are. And StatQuest gives an example of movie reviews. So how similar are maybe the sentiments of the movie review, or even the topic. What's going on in this picture? Describe what the table and graph means. Okay, so I think what's going on here is, so we have a phrase, hello world, and a phrase, hello. And we've put this in a table where each row and number represents the number of occurrences of hello and world in the phrase. So in this case, we have the first row 1 1, both hello world and world exist in the phrase, and this bottom row is just the hello that exists. So what we're doing here, it seems like we're trying to calculate the cosine similarity between these two phrases. And the way we've done that is we've plotted each phrase onto a two-dimensional graph, where a y-axis is the occurrence for world, x-axis is the occurrence for hello. Then we plot each phrase. Specifically, each point represents how many times each of these words appear in the phrase. And then finally, we just calculate the angle between them. So this is a 45-degree angle, cosine of 45 degrees. I think it's pi over 4, could be wrong. Yeah, I think it's pi over 4. Alright. So I think if these guys were perfectly the same, then the angle between them would be 0. The cosine of 0 is just 1. And so if you have a higher cosine similarity, that means your phrases are more similar. Okay. What is the main idea of a recurrent neural network? How do they work on a high level? Main idea is a way of constructing a neural network that can take in multiple sized inputs. The way you could do that is you kind of copy and paste the same stage or network multiple times through the process of unrolling, and there's a feedback loop that passes the output of one layer to the next unrolled layer. One, prefer using softmax in the multi-class classification setting for discrete labels over regression and one-hot encoding. So softmax gives you a probability. Regression, one-hot encoding, they both give you labels. Sometimes working with discrete labels, trying to convert them into continuous labels, it gets, or not continuous, but numerical labels. It's difficult, and sometimes there's some implicit ordering that comes into play when you don't want it. Okay. What is the maximum and minimum value that the cosine similarity can have? Why? So you can have max cosine of cosine of 0, which is going to be 1. I think the minimum value cosine similarity can have is cosine of pi, which is 0. So that's cosine of 180 degrees. Zero and 1. Oh shit, okay. I guess you can't have negative occurrences of a word. Was negative occurrences for and phrase that won't work out. So explain this image that shows a basic convolutional neural network stage. What this is showing is that we have one input image, we have k filters that are 5 by 5 by 3. I think what it'll do is it'll take one channel, 100, 100, 100, and then multiply by that together. Then you have channel 2, so 5 by 5, 100, 100, and then channel 3, 5 by 5, 100, 100. And then you add up all of those together, that'll give you a single feature map. Yeah, let me see. So how does the convolution step work with multiple channels? such a case, you have one 2D kernel per input channel, so you perform, which gives you a fine. Okay. Here's one input feature map. Maybe this is a question for ChatGPT. Seems to be some competing arguments. How does the convolution operation work a CNN when there's multiple channels? For example, if the input is 100 by 100 by 3, and we have a filter that is 5 by 5 by 3. Right. Okay, so it is summed across the depth as well. I'd imagine that we do this kind of channel by channel. Can you explain the element wise operation further? Does the 5 by 5 filter have the 3 filter same weights Okay, so it doesn't have the same filter, same weight across each channel. Okay, so I'm gonna actually add that stuff to here. This is very helpful. The input CNN is 100, but there are K filters that apply to what is going on mathematically. Okay, so mathematically, the filter gets applied across the input's image. In order for this operation to work, the depth number of channels for the filter and input need to be the same. The actual operation that takes place is a dot product between the corresponding elements, 5 by 5, bless you,
Thank you.
between the corresponding elements in the 5 by 5 by 3 image filter and the by 100 by 3 image. Okay. So the filter gets applied across the image. Input image. For this operation to work, the depth, number of channels for the filter, and input need to be the same. The 5 by 5 by 3 filter, 100 by 3 image. Okay. Can think of this operation as multiplying as between the corresponding elements in the in total, there will be 75, so 5 times 5 times 3 total multiplications that will get summed to a single value. That represents the output to the feature map. So to a single value, nice. Okay, that's good. Then I want to add maybe another question here. Add. Wait. Let's go to convnets and then maybe add here. So do the kernels filters have the same weights across multiple channels? No. Most likely not. Each channel represents a unique feature, and the weights that gets applied to it is different across the channels. Okay, gonna use the bathroom real quick. Probably be back in a sec, but I I think that was actually pretty helpful in understanding the intuition behind the convolution. I've been doing these flashcards for so long, but never really quite understood what was going on. So yeah, it's helpful. cosine similarity work? Okay, so cosine similarity mathematically is just a measure of how similar two variables are. I think you're just finding the cosine between the angle of two vectors, and the angle between the two vectors is represented by I think the two vectors are plotted onto a graph where the x and y axis is a measurement of how many times the word occurs in a phrase. So the vectors, they represent a phrase. And the x and y axis and the different types of axes represents how much is on represents how much is on the phrase. Okay. And the steps, I think there's probably 4 steps to think about. Right? Taking your phrase, counting the number of occurrences, plotting those occurrences, that phrase onto a graph, and then finding the angle between them and the cosine of the angle. Cosine similarity. It's just a way of measuring the similarity between two different phrases. StackQuest gives an example of movie reviews using cosine similarity to compare the similarity. What's going on in this picture? Describe what a table graph means. Okay, so this is a way of calculating cosine similarity for phrase of just 2 words, hello world, and then the phrase of just 1 word, hello. So we made a table of the word counts, we plotted the points, and then we figured out the angle between them, and then we calculated the cosine of the angle. Yeah. Okay, that's good. What is the maximum and minimum value cosine similarity you can have? Y. So the maximum minimum value is between 0 and 1. Y, 1 is the most similar. That means the two vectors lie on top of each other or go in the same direction. 0 means when the two vectors are orthogonal to each other, meaning they are going in opposite directions. Explain this image that shows a basic net stage of what's going on mathematically. So what's going on mathematically is we're applying a 5x5 kernel to a 100 by 3 image, and what happens mathematically is we kind of separate each channel and then apply the 5x5 kernel on each channel and we do that 3 different times. Then we take everything together, sum them all up, that becomes one value on our feature map. And we have k number of filters, so we do this k times, and we have k maps. I think what then happens is we have 100, 5 by 5. So if we want to have a output of the same size, 100, we go through this. I think we would need to have a padding of 2 And so that would ensure that the center of our image, of our filter, touches every single point on. Padding of 2 and a stride of 1 to get the 100-100 feature map. So the exploding/vanishing gradient problem with recurrent neural networks happen when you unravel and have a really deep network. The weights get applied exponentially onto your inputs, and so that causes them to either explode or vanish. So that means your earlier inputs will tend to get destroyed or will tend to vanish or explode, but the non-recent ones, or the more recent inputs, will tend to have a greater impact on the output. Did the kernel/filters have the same weights across multiple channels? No, they do not. Usually they don't, because each channel represents a specific feature. Then you have different weights that get applied to those channels or to learn those features. What does a ConvNet learn? So a convolutional neural network, they learn the weights on a filter or a kernel for their corresponding in each convolutional stage. Yeah, that's pretty good. To the input M by how many times depends on the stride, right? M by M by K. Sure. What is the idea of positional encoding? Positional encoding refers to transformers, and it's a way of encoding or describing the position of a token within a phrase to our network. And it's important whenever we have to deal with self-attention. Self-attention is an operation that calculates some type of score between a single token and the tokens that surround it in the phrase. Where's the formula to compute the cosine similarity directly from the table for counts? I think what you could do is you have I think what you could do is take the dot product between the phrase 1 and phrase 2 and the occurrences of each word and scale that by, divide that by the sum of the squared of that dot product squared, or maybe sum of the squared multiplications. So what does this do? I'm trying to think. This is like the length of vector A, length of vector B. And then you multiply the lengths together. I guess that makes sense. Length of vector. So wait, why can't we just add the lengths together? Why do we need to multiply them? It does create a new vector, right? So you project that down. I'm like trying to visualize what this projection will look like in my head. I'm having a hard time though. should it be? So the dot product, right, is how much A goes in the direction of B. B over B is kind of scaled, maybe to normalize it. Okay, yeah. I'm gonna skip that for now. Come back to this. Okay. Sequence to sequence. Sequence to sequence is a way to describe kind of this problem set of translating one sequence to another. For example, could be translating English to Spanish. Spanish. Context vector. Context vector is the output of the encoder portion of a neural network, specifically the LSTM. Specifically the encoder portion of a sequence model that uses LSTMs. And this is used to initialize the decoder portion of sequence model. What are two components of a generative adversarial network? What do they do? So the generative adversarial network is, I think, a way of creating generating new types of data or images. And so the key components here are first the generator and then the discriminator. So they're kind of fighting against each other in a little battle, and the generator is trying to trick the discriminator, and the discriminator tries to tell whether or not the image is real or if it's fake. Okay. When unrolling the LSTM and embedding layers, what happens to the weights and biases? They should be just the exact same. Do the kernels/filters have the same weights across multiple channels? No, they do not. Usually multiple channels represent different features that are supposed to be learned, so the weights there are different. Different channels. What is the game that's being played in a GAN? Right, so I think this is describing the idea of the generator is trying to generate a fake image, and the discriminator is trying to tell whether or not an image is real or fake. No, okay, GAN isn't really trying to generate a fake image, sorry. The generator isn't trying to generate a fake image, but an image that is indistinguishable from being real or fake. Okay, the generator wants the error rate to be high, maximize, and the discriminator wants the error rate to be low, minimize. Okay. So what is going on in this photo? Describe what each component means. What's going on in this photo? You have a word embedding model that is trying to embed the phrase "let's go to," and then at the end of sentence token. So what this does is it'll create two embeddings, one here, and the embeddings themselves can be either thought of as the weights or the outputs of the activation. What are tokens? Tokens are just kind of like a small unit or a unique symbol that appears usually in the context of phrases, sentences with language. They could be a character, a symbol, like an apostrophe, or even the ampersand symbol, and are just small little units that are fed into big, large language models. And which elements in a vocabulary. Okay. In theory, if a GAN is run forever, then it will end up generating images or something that is indistinguishable between being real or fake. 50-50. Okay. Is that really real? At that point, we have a pretty good generator that will create images that look really real. Okay, what is going on in this photo? Describe each component. So this is a encoder portion of a sequence model. You have two different layers, an embedding layer, and then also a LSTM layer. So what you're doing is you're passing in the phrase "let's go" to the first embedding layers, and then those embeddings are passed into the LSTM layers. And then this will encode the phrase "let's go" to hopefully something that our network can learn from, and it'll spit out a context vector that we passed and initialize the decoder portion of our network. The word embedding layer embeds the sentence "let's go" into two embeddings that get fed into the LSTM unit. Okay. That's the sentence "let's go" into two embeddings that get fed into the LSTM unit, right? Oh, so it takes in two embeddings for each token, then codes the embedding one token at a time. There are two LSTM neural units per token. Okay. Alright, and then the first LSTM word embedding layer encodes the word "let's," which gets passed to the next underworld layer that codes "go." Maybe layer isn't the right word, but unit. Okay. What is the formula to compute the cosine similarity directly from the table of word counts? So it's just the scale dot product between the number of occurrences of each word in the actual dot product between the occurrences of each word in the phrase, scaled by the length of the vector. which is multiplied the norm of L2 norm of A and the L2 norm of B, the product of that. Okay, I think that's pretty good. What is the game that's being played in a GAN? So in a general adversarial network, the game that's being played is a min-max game between our generator, discriminator. Our generator wants to maximize the loss of the discriminator. Discriminator wants to minimize the loss that it makes. The loss here represents the error between the prediction of whether or not the generator is making a real or fake image. Okay. What is going on in the photo? Describe each component. So this is the encoder portion of a sequence-to-sequence model. Specifically, it has 3 different layers: word embedding layer, 2 LSTM layers, and each layer has 2 LSTM units for each token. The token here is let's and go, and each long-term memory, short-term memory are all encoded, are all initialized to 0. Only short-term memory travels between LSTM layers and units in the same layer. Okay, so yeah, only short-term memory travels between the different layers. Long-term memory stays its course. What is the input to the generator in a GAN? The input is just random noise. It could be a vector of randomness, and generator will use that vector to try to reproduce some type of image. The way I'm thinking about the input is that it's a random point in a vector space. Okay. In theory, what would happen if a GAN is run forever? In theory, the GAN will get to a point where the generator will create an image based off some noise, and then the discriminator will always output 0.5. So there's a 50% chance that it's real, 50% chance that it's fake. In that case, the image that the GAN makes is kind of completely indistinguishable from being real, being fake.
currently living with my girlfriend now, and I noticed something that was wrong. For my discussion activity, grades are used in public health. I did not submit the assignment, but I did the 10th class, so I think it should be.
So what are the T components of a general adversarial network? What do they do? So one component is the generator. It just generates images. Second is the discriminator. It tries to tell whether or not the image that the generator made was real or fake. What is the formula to compute the cosine similarity directly from the table of word counts? You just take the dot products, so the sum of the product between the elements divided by the product of the L2 norms of each of the respective vectors.
Just wanted to know when it was due. And
Okay.
we will talk about
What are tokens? Tokens, just a basic unit that represents a single kind of symbol or character in a vocabulary. What is the input to the generator? And again, this is just a vector of random noise. Random numbers can be thought of as a random point in space. What is the game that's being played? And again, so you have a generator, discriminator, min-max game. Generator is trying to maximize the misclassification or the error rates for the discriminator, and the discriminator is trying to minimize that error rate. This picture with the tokens, let's to go and the end of sentence token. What is the latent space? Oof, this one's tough. I think the latent space could refer to the mapping of one vector in a vector space that is input into the generator, how that maps from that vector space to the output space, which is, we can think of as maybe a vector or a matrix that represents an image. So I think maybe to ground that in a better example, let's try to say that we have a general adversarial network that tries to create images for a cat. Then our generator will input some noise. This could be a random vector in some vector space that's n-dimensional. Let's say that one of the things that the generator learns is for some of the vectors that are input into the generator, it notices that, let's say, one of the dimensions tends to correlate with the color of the cat's hair. So maybe there's kind of this injective one-to-one mapping between the value of that dimension and then also the color of the cat's hair. I think that refers to the latent space. Yeah. So this is a pretty complex topic that I'm not entirely sure. I'm gonna come back to it. Alright. What is this image showing? Why do the flat rectangles become cubes? Then long rectangles in the bottom half of the image. This is a convolutional neural network. It will take in these images and then also filters will then expand the feature maps and shrink the spatial dimensions. In that case, it helps with training so that you don't have a bunch of parameters to train. And then also, I think this helps you learn more features if you were able to increase the size of the feature maps. Excuse me. Okay, so this operation is also known as pooling. Right? What are some benefits and drawbacks of pooling? So some benefits of pooling could be the fact that you can, 1, reduce the number of parameters to train, and 2, maybe helps learn spatial invariance. Drawbacks, you lose a bunch of information when you aggregate a lot of things together, and then also some people disagree with the learning of spatial invariance. Drawbacks of pooling, Yeah, I think those are probably big ones. Makes training difficult for certain tasks. So generative, I think this has to do with the loss of information. Okay. Generative models for pixel models. Yeah, I'd say that's hard. Ooh, so precision versus recall. So I think precision is a measure of how many things are you getting right relative to the guesses that you've made. This is slightly different from recall, was out of all of the possible right answers that you're getting, out of all the possible right answers, how many right answers are you getting? So usually with high recall, you tend to have lower precision. No, actually, maybe that's not right, but let me try to reword this. So what I'm thinking in my head right now is you have a Venn diagram or a circle. A circle is split in half, right? First half is positive, second half is negative. Then you have this circle enclosed in a little square box. I think the left half of the box is positive, right half of the box is negative. The box represents the true output space. The circle represents what your prediction is. I think precision then is a measure of the true positives that you make relative to the true positives and true negatives that exist in the or maybe false positives. Let's see. To all of the positive. Oh, shit. Okay. So it'll be false positives and true positives. So another way of saying that is the number of true guessed relative to the number of true and false positives. Is there another way? Okay. Yeah, that's hard. Why are word embeddings important? Word embeddings are important because they help us first convert words into numbers, which then can be passed into a neural network, and two, can help us learn the context, or really help a neural network learn the context of words in a sentence. I guess when I refer to word embeddings, maybe the neural network word embedding. Okay. Common problems associated with translation. Usually sentences in one language are different size compared to a different language. So you have different sized inputs. Yeah, and the words themselves can be put into neural networks. What is recall? How is this different from precision? Okay, so we had defined precision as the ratio of true positives to the number of true positives and false positives. Recall, on the other hand, is a measure of maybe true positives. Divided by the I want to say true positives and true negatives. Okay, right. I think I need some mathematical formulas here. Let's say it's hard. In theory, what will happen if a GAN runs forever? Generator becomes so good that discriminator will always just output 0.5. People make word embeddings that could be hundreds, if not thousands. Spatial invariance. The position of an object doesn't affect the classification of that object. Oof. Intersection over union. What is its use in object detection? So IOU,
You gotta be kidding me.
Right, so it's intersection, so how many maybe pixels exist in both over the total amount of pixels that exist in the image. What is its use in object detection? So what I'm thinking of object detection is just putting boxes around different objects. Intersection over union could be thought of as you have the ground truth, which is the box that perfectly represents, let's say, a cat. And then you have your guess, which is a box that what you think would represent a cat is. To measure the accuracy or the intersection over union, you see how much overlap those two boxes have on each other. And if there's a lot of overlap, that means your intersection over union is really high. If there's little overlap, that means your intersection over union is really low. Yeah, mathematically,
Anyways.
that's tough. Okay. Input to the generator again, it's just a vector of random noise. It can be thought of as a point in a vector space. Dot product vectors divided by the product of the length L2 norm of both vectors. Okay, that's good. Full zero padding, how do we find the amount of padding we should use? Full zero padding is the idea where you add enough padding so that your filter, every single point on your filter is going to touch every single point on the image. So how do you actually do that? You just have to add n minus 1 padding on each side, where n is the number of n is the size of the filter itself. So if we have a 5x5 filter, we add 4 padding on each side of the image in order to ensure full zero padding. And this usually creates a higher spatial dimension for the feature map. Okay. What is self-attention? Oh, how does it work? Give supporting example. Okay, self-attention. This is kind of like the superpower of transformers. Big idea, stemming from the concept of attention. I think attention is a way of measuring how similar different tokens or phrases are in a sentence. And self-attention compares all these different words or tokens to itself. Okay, so how does it work? With a transformer, the self-attention block has kind of three different things. You have a query, a key, and a value. I think what's going on here with the query and the key, you have your input token, and from this you have different linear activations, and these create the query, key, and value vectors. So you're not actually modifying your input at all. The query, I think, is trying to answer, what am I looking for? The key is maybe offering or answering, what do I have to give? And what'll happen is, in order to calculate the self-attention, you take your query, so what does your input have to offer? You multiply it by, you take the dot product between the keys of each token. The keys represent kind of, okay, what do I have to offer? So you're querying each key, I guess you could say, but you're really taking the dot product. And you also include the key for the token that you're currently working on. And then for each of these dot products, then you feed them through a softmax function. So softmax will normalize, will make sure that every input is between 0 and 1, and I think we'll eventually add up all of these self-attention values, and that will just equal 1. Actually, these aren't the values themselves, so these are kind of the weights that we use to calculate the self-attention value. So yeah, the last step is kind of the value vector, which is just another linear activation from the inputs. We take that value vector, we multiply it by every single softmax output for every single one of the tokens. Oh wow, so this isn't even at a high level. Okay, at a high level, it's a way of keeping track of the relationship between words. Pizza came out of the oven and it tasted good. In the sentence, it could associate with pizza or oven. In general, self-attention works by seeing how similar each word in a sentence is to all the other words in the sentence, including itself. Okay. What is precision? Alright, so I think this is where, what is the mathematical definition of precision and recall? Okay, false names. False positive carry high here. Okay, so this actually does help a lot. is it mathematically? Oh shit. Refers to the measure of how many true positives. How many true positive? Another way of saying this. Yeah, this is probably the wrong compared to the maybe because alright, let's see. The total predicted positives change to make more predictions. I see, so it does change kind of. So, right. Mathematically, precision is defined as, so we have true positive plus false negative, false positive. Chat GPT says that precision is answering of all the instances. Okay. Yeah, honestly, this image confuses me even more. Selected elements, true positives, false positives. So this is the oops. What is precision? What question is it answering? What is it mathematically? Okay. I'm gonna also add something here. Put this in object detection. Alright, so does the precision change as a model makes more classifications? Yes. Precision changes as a model makes more classifications. Because precision depends on the number of predictions and the outcome of those predictions. Okay. Right, so I guess if what are those? So I guess if you were to make false negatives and true negatives, false negative and true negative predictions, our model wouldn't care for precision. But if it were to make more positive predictions, then that'll increase or decrease the precision. Yeah. If the model makes a false positive prediction, so this could be the saying a cat is a picture is a cat even though it is not a cat, then the precision falls. If the model makes a true positive prediction, what would happen to the precision depending for different types of predictions? Saying a picture is a cat when actually is a cat, then the precision will stay the same or increase. Right, precision will stay the same or increase. Okay. So I'm gonna modify this maybe. Note that precision does change over time as the model makes more predictions. Okay, I think that's the key thing to know, that precision does change whenever the model makes more predictions. Okay. Oh, shoot. So what is precision? What question is it answering? What is it mathematically? I'll try to answer this without looking at what I wrote down. But precision at a high level, it's a measure of model performance, model accuracy, and really it's a measure of how many correct positive guesses, predictions did your model make relative to all of the positive predictions that your model had made. Oh man, okay, so I think the question it's trying to answer is how well am I making a positive prediction relative to the number of positive predictions I've made. So of all the instances we predict as positive, how many are actually positive? And then mathematically, precision is defined as the true positives divided by the true positive plus false positives. Okay, and precision over time does change over time. Yeah. I'm gonna add an S here because these are not single. They're not singular. I think maybe relevant elements. Oh, so false negatives, true positives. Everything here is going to be a positive, and all of these here are negatives. I see. Okay. Say hard. Latent space. It's the mapping between your input noise and then also the output image. Okay. What is recall? How is it different from precision? Maybe provide an example. So recall is a measure of so the true positives think divided by the true positives and false negatives. And true negatives. Right. Oh. Okay, if it is true positives and false negatives, So, okay, what is recall trying to answer? What question is it trying to answer? I think it's a measure of, okay, your model is making predictions. How many of those predictions are actually right, maybe? Okay, so precision was trying to answer of all of the positive predictions, how many of those are actually positive, right? How many of them are actually truly positive? Recall is, out of all the predictions that you've made, that's out of all of the positive predictions that you made. So this is all of the true positive predictions. Maybe this is out of all of the true positive examples. How many did you end up getting right? Okay. Okay. Does recall also change as the number of predictions increase? So let's see the precision recall graph. I feel like understanding this dynamic is really important. So why is it that as you increase your recall, your precision tends to fall? So, let me try to find, let's just do this one. So we have true positives over false positives and true positives here. And then this is true positives divided by true positives and false negatives.
I literally completely forgot we didn't have class. That's why I literally, that LIC project where we all talked about what we did, that was not due that day. We did it the next week.
So if this is 0, that means yeah, let me think. So that means we have 1 true positive. And I feel like the recall would also be the same, would it not? Because we have true positive of true positive. So it'd be 1 over 1. All right. Because this would be true positive divided by true positive. It would be 1 divided by 1. And I feel like for a recall, it'd also be 1 divided by 1, right? We have 1 true positive. Let's say precision false, so that means we have 1 false positive. So let's say it's 1 over 2. Okay, so there's this false negative term that we haven't gone to yet. I'm gonna ask, so why is precision and recall negatively correlated? Some training, some of the actual positive examples are predicted as true. False negatives are decreased by false positives. Damn. Alright, people are roasting each other. Okay, so yeah, there's a bit of complexity here. Okay. So I think maybe what I might do is see if there's a StatQuest video. There's ROC, receiver operator, and a curve. Cool. Yeah, I'm gonna take a look at these two videos and see if there's anything interesting here. So I think this is probably where I might end the stream. I still have a few of these flashcards to go through, but I think we've stopped at a pretty good point. Yeah, we stopped at a pretty good point where we talked about some GAN stuff and also transformers, a little bit of transformers. Refreshed on convolutional neural networks, helped I finally understand how the convolution operation works across multiple channels. So I think that was pretty important. But now I'm kind of getting stuck on the ideas of precision and recall. So I'm gonna try to watch a few videos, catch up on that, and maybe I'll stream again later in the day. So see you guys in the next one. Peace.